Section 9.1 is sequences. Now most of Chapter 9 deals with series, but before we can talk about what a series is, we need to define a sequence. So in this section, we're going to be looking at what is a sequence, what is the limit of a sequence, and some other properties and theorems that have to do with sequences. Let's begin by defining what a sequence is. We say that a sequence is a function whose domain n is a set of positive integers or natural numbers. What that means is that the numbers that you plug in, right, the domain, what you plug into the sequence are things like 1 and then 2, 3, 4, 5, etc. Those positive integers are natural numbers. This is the domain of your sequence. You can also think of a sequence as a list where order matters. So a sequence is just going to be a list of numbers where for your first number you inputted a 1, your second number you inputted a 2, your third number you inputted a 3, etc. The nth term of a sequence, that is denoted by a sub n. And then the entire sequence, if you're trying to look at what the formula for the sequence is, it's given as a sub n in these braces. This gives you the formula for your sequence. Let's do example 1, where we're looking at writing the first 5 terms of the given sequence. We're told that our formula is 2 to the n minus 1 all over 2 to the n. And we want the first 5 terms of the sequence. So let's start by finding the first term. Well, our first term is going to be when n is equal to 1. Therefore, a sub 1 is going to be 2. Instead of n, I write 1 minus 1 all over 2. And again, instead of n, I write 1. 2 to the first minus 1 over 2 to the first. And that gives me a half. A sub 2. Now what we're doing is plugging in a 2 for our n's. That's going to be 2 to the second minus 1 all over 2 to the second, and that reduces to 3 over 4. A sub 3, now my input is 3, 2 cubed minus 1 all over 2 cubed, and that is 7 over 8. A sub 4, 2 to the 4th minus 1 all over 2 to the 4th is 15 over 16. And then the final one that we're looking for, a sub 5, is going to be 2 to the 5th minus 1 all over 2 to the 5th, which is 31 over 32. So the first 5 terms of this sequence, if I have a sub n, the first 5 terms would be 1/2, comma, 3/4, comma, 7/8, comma, 15/16, comma, 31/32, comma, dot, 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 all the way to a sub n if I'm listing it with a sub n. So a sub n is just going to be that general term, but the first 5 terms in this particular sequence are these 5 terms. Again, this happens when n is equal to 1. When n is equal to 2, we get 3/4. When n is equal to 3, we got 7/8. When n is equal to 4, we got 15/16. And then when n is equal to 5, we got 31 over 32. Again, you can see that a sequence is just a list of numbers where order matters. One of the main things that we are going to be concentrating on in this section is what the limit of a sequence is. We say this: if L is a real number and f is a function of real variables such that the limit as x goes to infinity of f of x is equal to L, then if our sequence a sub n is a sequence such that we can rewrite this sequence as a function for every positive integer n, then the limit as n goes to infinity is equal to L. What this means is that because we define sequences to be a function, we can use our knowledge of limits to find the limit of a sequence. So think of the limit of a sequence as when I'm listing all these numbers out, am I approaching a value? To determine if the sequence is approaching a number, we have to take the limit as n goes to infinity. If that limit exists, if you end up with a number L, then this sequence is a convergent sequence, which means your sequence converges, it's approaching a value. If the limit does not exist, so if you end up with positive or negative infinity, or just does not exist, then your sequence is a divergent sequence. So you're not trying to approach a number. Maybe you're just oscillating between two numbers or just increasing or decreasing without bound. Let's review some properties of limits of sequences before we look at examples where we determine if a sequence converges or diverges. If I tell you that the limit as n goes to infinity of a sub n is equal to L, and that the limit as n goes to infinity of b sub n is equal to k, the following four properties hold. The first one, the limit as n goes to infinity of c times a sub n is just equal to c times the limit as n goes to infinity of a sub n, or c times L, where c is just any real number. Basically, this is telling you constant multipliers multiply along. The next one, the limit as n goes to infinity of a sub n plus or minus b sub n is just going to be the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n, or L plus or minus k. The second one just says that you can take the limit of a term at a time over addition and subtraction. The third one allows you to break up limits over multiplication because it says the limit of the product a sub n times b sub n is equal to the limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n, or you can think of it as just L times k. So for limits, you are allowed to split them up over multiplication. You're also allowed to split them up over division. We know that the limit as n goes to infinity of a sub n divided by b sub n is just equal to the limit as n goes to infinity of a sub n divided by the limit as n goes to infinity of b sub n, or L over k. And this is going to be where b sub n isn't equal to 0 and k isn't equal to 0 because we know division by 0 is undefined. These four properties should make a lot of sense. All they're saying is 1. Constant multipliers multiply along, and then 2, 3, and 4, that you can separate limits over addition, subtraction, multiplication, and division. Let's keep going to the next four examples where we're trying to determine the convergence or divergence of the sequence given the nth term, and then it says if the sequence converges, find its limit. To determine if your sequence converges or diverges, what you need to do is take the limit as n goes to infinity of a sub n. If that equals some number L, so if the limit exists, then that means the sequence converges. If the limit does not exist, then that means that the sequence diverges. We're just trying to determine when we're listing out these numbers, are we approaching some number? If the answer is yes, our sequence converges. If the answer is no, our sequence diverges. Example 2 is a sub n is equal to 2 to the n minus 1 all over 2 to the n. To determine if this sequence converges or diverges, I need to take the limit as n goes to infinity of a sub n, which is 2 to the n minus 1 all over 2 to the n. Well, what is the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n? Well, it's currently 2 to the infinity, which is just infinity, minus 1, or just infinity, divided by 2 to the infinity, which is just infinity. So this is infinity over infinity. If we have infinity over infinity, we can use L'Hopital's rule to assist us in finding the limit. We need to take the derivative of the numerator and the derivative of the denominator. Well, let's recall how to take the derivative of an exponential function. Recall from Calculus 1 that the derivative of a number a raised to a power u was equal to a to the u times the natural log of a times u prime. So in this case, the derivative of 2 to the n, well, this is my a and this is my u, would be 2 to the n times the natural log of 2 times the derivative of n. Well, the derivative of n is just 1, so I don't need to write that. And then what's the derivative of negative 1? Well, the derivative of negative 1 is 0. Again, I don't need to write that. Now take the derivative of the denominator. Well, it's also a 2 to the n, and that's going to make it a 2 to the n times the natural log of 2, because it's an a to the u times the natural log of a times u prime. Again, here u is equal to n, and the derivative of n is 1, which is why we aren't writing times 1. Well, now, notice we have the exact same thing in the numerator and the denominator, so our 2 to the n's cancel, and our natural logs of 2 cancel, and all we're left with is 1. What's the limit as n approaches infinity of 1? Well, that's equal to 1. So when we took the limit here, we ended up with a number. Therefore, we know that our limit exists. Since our limit exists, we can say that our sequence converges. Now, what this means, again, is that as you're listing the numbers for this particular sequence, you're getting closer and closer and closer to a number. The number you're approaching is 1. Let's look at example 3. I have the sequence a sub n is equal to 2 to the n plus 1 over 1 plus the cubed root of n. If I'm trying to determine if this sequence converges or diverges, I have to take the limit as n goes to infinity of the sequence of 2 to the n plus 1 over 1 plus, instead of writing that as the cube root of n, I'm going to write it as n to the 1/3 power. Well, what does that equal? Well, that's going to be infinity over infinity again. So that means I can use L'Hopital's rule. But this is a limit at infinity with things that are kind of polynomials, because n to the 1/3 technically isn't a polynomial. But because they're both n to a power, I'm just going to do it the way that we learned in Calculus 1. I'm going to look at the leading term in the numerator, which means the term with the highest exponent, and the leading term in the denominator, again the term with the highest exponent, and I'm going to rewrite the limit just putting those two over each other and then reducing. So this becomes 2n to the 2/3. And now I'm going to take the limit again. Well, what's the limit as n goes to infinity of 2n to the 2/3? Well, that's going to equal infinity. Since I got infinity and we know that that means that my limit does not exist, that means that this sequence diverges. Again, what you want to think there is when I list out the numbers for this sequence, my numbers are either getting infinitely bigger or not approaching a value. Let's do number 4. Example 4 is a sub n is equal to n over the natural log of n. The first thing you have to do is figure out what the limit as n goes to infinity of your sequence is, n over the natural log of n. This is still currently infinity over infinity. Unlike example 3, this is not n to a power divided by n to a power, so we're going to use L'Hopital's rule to evaluate this limit. If we use L'Hopital's rule, what is the derivative of the numerator? Well, the derivative of n is 1. And then what's the derivative of the denominator? Well, the derivative of the natural log of n is 1 over n. Now we clean it up before we try to take the limit again. Well, this is really just 1 divided by 1 over n, and if you're dividing by a fraction, that's the same as multiplying by its reciprocal. Therefore, you're really just looking at the limit as n goes to infinity of n. Well, that's just going to equal infinity. Since that means that the limit doesn't exist, we know that this sequence diverges. Let's look at number 5. We have a sub n is equal to 1 plus 1 over n to the n. The first thing we do is take the limit as n goes to infinity of the sequence. So we're looking at 1 plus 1 over n raised to the nth power. Well, what does that equal? Well, that would be a 1 plus 1 over infinity we know is 0 raised to the infinity, or 1 to the infinity. This is that bad indeterminate form. And remember, if your indeterminate form was exponential, what we had to do is we had to let y equal the limit. If we say that y is going to equal the limit as n goes to infinity of 1 plus 1 over n to the n, in order to remove the exponent, what we had to do was take the natural log of both sides. So we will take the natural log of the left, the natural log of y, and that's going to equal, and remember, instead of taking the natural log of the limit, we said that we were going to write this as the limit of the natural log. Now we get to use our power to product rule and take this n and have it multiply the natural log. So this is equal to the limit as n goes to infinity of n times the natural log of 1 plus 1 over n. Well, now what am I looking at? Well, this is going to equal infinity times, and this is just going to be the natural log of 1 plus 0, or the natural log of 1, which is 0. this is still a bad indeterminate form. I need to move one of these terms. I either need to move n or I need to move the natural log of 1 plus 1 over n. It is going to be easier to move n because I can move that just by making it a negative exponent. If I put it in the denominator by making it a negative exponent, I have the natural log of 1 plus 1 over n, and then the other one becomes n to the negative first. We know n to the negative first is equivalent to saying 1 over n. Therefore, I'm really looking at the limit as n goes to infinity of the natural log of 1 plus 1 over n divided by 1 over n. Well, now what are we? We are now the natural log of 1, which is 0, over 1 divided by infinity, which is 0. Since we're 0 over 0, what we can do is use L'Hopital's rule. Bring this guy down. So the natural log of y we know is equal to the limit as n goes to infinity if I take the derivative of the numerator. Well, the derivative of the natural log of 1 plus 1 over n is going to be the derivative of the argument. So the derivative of 1 plus 1 over n, well, the derivative of 1 is 0. And again, I know I can write this 1 over n as an n to the negative first. So if I take that derivative, that's just going to be negative n to the negative second. So it's the derivative of 1 plus 1 over n over itself, 1 plus 1 over n. And then the derivative of the denominator, 1 over n, again, think of it as an n to the negative first, it's just a negative n to the negative second. If we're trying to clean this up, we know that this is just negative n to the negative second over 1 plus 1 over n times the reciprocal of this, because if you're dividing by it, you need to multiply by its reciprocal. And the reciprocal of negative n to the negative second, since it doesn't have a denominator, is just going to be 1 over negative n to the negative second. Well, now we notice that our negative n to the negative seconds will cancel, and all we're left with is the limit as n goes to infinity of 1 over 1 plus 1 over n. Now if we take the limit, we end up with 1 over 1 plus 0, or just 1. That means that the natural log of y is equal to 1. But I don't want the natural log of y, I want what y is because that was my original limit. In order to figure out what y is, I make e the base, and I have e raised to the natural log of y equals e raised to the first power. These will cancel, and that means that y is equal to e. Therefore, we know that that meant that the limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to e. Since we were equal to a number, that meant that our sequence converges. So the limit of this sequence was e, which means that the numbers in this list are approaching e. For number 2, the limit of that sequence was 1 because the numbers were approaching 1. Number 3 and 4 diverged, so they didn't have a limit of the sequence.